Hello, my name is Scott Grizzard from the University of South Florida. This is Calculus 1, Lecture 3B, Continuity in the Intermediate Value Theorem. So last time we talked about limits at and to infinity. One thing I did not cover in that lecture was ambiguous infinitesimal. So we'll do that first, and then we'll talk about continuity and the intermediate value theorem. We'll show a formal definition of continuity. We'll do some examples about showing a function that's continuous. Then we'll do some psychotic things like a function that's continuous at exactly 1 point, which is kind of weird and different from what you did in peer leading. And then we'll talk about the intermediate value theorem. Next time, we will be talking about the definition of the derivative, which is probably the most important lecture of the course, at least for module 1. All right, so let's talk about real fast. Let's cover ambiguous infinitesimals. So if we consider this function, the limit as x goes to 1 of 1 over x squared minus 2x plus 1. And I get 1 over 0 for that. Now, if I try to stick in 1 minus or 1 plus, either one, if I try to stick in 1 minus, I wind up with 1 over 2 minus 2, 2 left minus 2 left. And that is an ambiguous thing. You're not sure which one of those is the stronger left. If you look at this, you can kind of see, your intuition would say, oh, I don't know here. I mean, this, if I sub in 1 left here, and then I'm squaring it, but then I'm multiplying. So there's some kind of idea, maybe one of these 2 lefts are more powerful than the other. Okay? But which side of the 0 am I actually on? Well, if we factor this and we put it into x minus 1 squared form, we can actually see that. Okay? So now once I factored it, I put in my infinitesimal and I get 1 over 1 left minus 1. Well, that's going to be 0 left squared. And 0 left squared, remember that's a slightly negative number. I square it, I get a slightly positive number. Okay. Likewise, I put it in here and I get 0 plus, but then I square it. And I see here that this is infinity and infinity. So this does have a limit. But in order to get at that, I kind of have to factor. I may have to complete a square if it wasn't a nice thing that already factored as a square. So sometimes when you play with an infinitesimal, you have to fiddle with it to see about these ambiguous things. So that's one thing I didn't cover last time. So in general, for a greater than 0, the ambiguous ones are a left minus a left, a right minus a right, and a left plus a right. You're not quite sure where they're going to wind up, so you need to be careful around those. Okay, so let's look at continuity then. And peer leading, continuity was draw it without lifting your pencil. So, for example, in the classic example that we're going to be working with here is f of x equals the absolute value of x. Now, this right here is the definition of absolute value. And you're going to want that because this is going to be one of our key examples in the next lecture about something that is continuous but not differential. All right, so you're going to want this later. So just keeping that in mind for later, we're actually going to want to use this example. This example is kind of nice. Okay, so here, if we look at this, if I take the absolute value, right? So if I take the absolute value of -1, what I'm going to do, because I want, this negative x is somewhat weird. Remember, x is a negative number. And if I take a negative number and multiply it by -1, I get its positive side. So this idea is that I'm going to multiply a negative x by -1 to get a positive number. So this is a precise definition of the absolute value. Okay? If I'm negative, I simply multiply it by -1. Negative times negative is positive. Okay? And if you look at the graph, that's kind of, if you graph negative x here, and you look at the graph of absolute value of x, you'll notice that negative x and absolute value of x have the exact same graph if I'm less than 0. Right? They've got that slope of -1 all the way down. So that's how you can think about this. So this is a continuous function. All right, I can draw it without loosening my pencil. This is something that's not continuous, right? I've got a wholly function. This has a whole. I might have a singularity or something that's infinite in the middle, and I might have a jump. So this is called a jump discontinuity, all right? So I've got a whole discontinuity. I've got a singularity, which is, something that shoots down to infinity, negative infinity, or up to positive infinity, somewhere in the middle. And then I've got these kind of jumps. These are the things that are not continuous or discontinuous, okay? So we can think of f, right? A continuous function is one that is an atheistic white boy, all right? It's atheistic. It doesn't like things that are holy. It doesn't like things that are infinite. And it's a white boy. It can't jump. So this is what f is. F is continuous if f is an atheistic white boy. Nothing holy, nothing infinite, can't jump. Okay? So that's a way to remember this. All right, so now let's talk about a more precise definition. If we want a more precise definition, let's let f be a function defined on some interval d. And let's let a be a number in the interval. F is continuous at a if the limit as x goes to a of f of x equals f of a. And that's the whole definition. The limit as x goes to a of f of x equals f of a. So when I ask you for the definition of continuity on a quiz, this is what you need. The limit as x goes to a of f of x equals f of a. It's a very short definition. It's got a lot packed into it, though. So if we wanted a working definition, which is different than a formal definition, although the working definition will work when someone asks what's the definition of continuity at a point, the working definition is that f is continuous at x equals a if f is defined at a. See here, f is defined at a. If I look at this one here, if this was a, here, f is not defined at a. So this would be discontinuous at a. F needs to be defined at a. The limit as x goes to a of f of x equals f of a. Right? So here, this fails that definition. Because as I come from the left, here's f of a. But the limit from the left is fine, but it's not defined there. And the limit from, right? So the limit of as I go toward a, it's not the same thing as f of a. Same thing here. As I head toward a, the limit from the left does not equal the value of the function. Okay? Likewise, the limit as x goes to a from the right needs to equal the value of the function. So as you can see here, the limit from the left equals the limit from the right equals the value of the function. So here, right here, is f of a. Okay. So that's kind of so here is the packed, compressed version right here. The limit as x goes to a of f of x equals f of a. But the working definition has these kind of three parts that you have to check. Okay. So, for example, I want to prove that f of x equals the absolute value of x is continuous at x equals a. So what is it I want to show? Using the definition of the absolute value of x, which is this, I want to show that the limit as x goes to 0 minus of f of x equals f of 0, and the limit as x goes to 0 plus of f of x equals f of 0. Right? And then I also need to show that it's defined, but it's defined. Okay? So my body here. What's the body here? So I say what f of x is, what absolute value of x means. Now, f of 0 equals 0. Right? I plug it into that formula. I've got something defined. Right? I can even say that. Okay. Now, what I need to show is that the limit from the left equals the limit from the right equals the value of the function. So what do I need? I need the limit from the left, limit as x goes to 0 of f of x equals. Now, if I'm less than 0, I'm going to use this part of the definition. Okay. So since I'm less than 0, I'm using this lower part of the definition. Okay. Thus, okay, so that's true. Now, right, so I sub in here limit as x goes to 0 left of negative x. I directly sub in because negative x is a perfectly good polynomial. And I get negative 0, which is, of course, 0. So the first part of the definition is met, right? I've done the thing I need to show first. Okay. Let's go ahead and add to our strategy here a little bit so that we've said these other things. Right, so the three things I need to show from our working definition. Okay, so I said that f of x equals this. This is f of 0 equals this, so this is defined. And I've shown the first bit. Okay, so now what I'm going to do is I'm going to say, okay, well, the limit as x goes to 0 from the left, I already said that, equals 0. So that's true. I'll leave in a little mark. First bullet. Second bullet. And now the third thing, I need to show that the limit from the left equals f of 0, the right equals f of 0. So that's just the identity function because I use the right definition. So the limit as x goes to 0 plus of x. So here I use the left definition. Right, so here I use the right definition. And here I use the left definition. All right. So I've used the negative x, and so here I use the negative x, here I use the positive x. And then I showed the three things. So this is the third bullet. So f is continuous at x equals 0. And you know what? I feel like crowing a little bit. Right? So I've gone ahead and I proved this, right? I want to prove this thing is continuous, so I just need to show it meets the definition. So I need to show that it works the meeting definition, and those are those three things, right? F of a is defined. The limit as x goes to a from the left of f of x equals f of a. The limit as x goes to a from the right is of f of x equals f of a. And notice that this right here, I could use this definition, but this definition, I just have to unpack it a little to get this. Okay. Let's look at another example. Let's consider f of x equals x cubed if x is greater than or equal to 1, x squared if x is less than 1. Is that continuous at x equals 1? Well, what are the three things I need to check, right? I need to say, first of all, if it exists, then, so this is actually up here. Oops. This would be the first thing to check. Okay, so the things I need to check are that f of 1 exists, f of 1 equals 1 cubed, according to my definition, equals 1. Then I need to check that the limit from the left equals the limit from the right, equals the value of the function. So the limit from the left of f of x equals the limit as x goes to 1 of x squared. Again, I'm using the, I'm less than 1, which equals 1 squared, which equals 1. And then I should say that equals f of 1. The limit as x goes to the right of, as x goes to the, as 1 from the right is f of x equals the limit as x goes to 1 right of x cubed, because I'm now greater than 1, equals 1. So the limit from the left equals the limit from the right equals the value of the function, and f is continuous at x equals 1. Again, that's a nice little proof. I didn't write an introduction and all that. I just said check those things, which is an introduction in itself. All right, so another example. Here's a function that's actually, oops, there's a mistake right here. So the function sine 1 over x is not continuous. Oops, that actually was right. Yeah. So, yes. So I had it right, and then I thought it was wrong, but it's not. So this function right here, f of x equals sine 1 over x if x does not equal 0, and 0 if x equals 0, is not continuous at x equals 0, because these limits don't exist. However, remember, if I multiply the top by x, then I've got this g of x equals x sine 1 over x if x equals 0, and 0 if x, if x does not equal 0. This actually is continuous because I've taken that big wavy thing and I've kind of plugged in the thing that was missing. So the limit as x goes to 0 from the left of this g of x equals 0, because I did that by 2 cops. And I did that in the previous lecture if you want to go check it out. And likewise from the right, I've got 2 cops, not the previous lecture, 2 lectures back. So that means that g of 0 equals 0 from the above definition. So this is continuous. But I can't really draw that without lifting my pencil. It's a little bit trickier. So it's a little bit different than the one that we had before. If I want to look at the graph of this, let's turn this off. So this is sine of 1 over x, right? So remember that, not like that. Look, it's sine 1 over x. So we want to look at this, and we see that sine 1 over x, you know, I don't have a limit at all, even if I try to put that thing in the hole. So if I put on here 0, 1 as a point. All right, so I put on 0, 1 as a point, and it still doesn't help. Even though I've got a point here that's defined at 0, 1, there's still no limit as I go to 0 from either the left or the right. But if I multiply this by x, remember, I get that kind of, I get this behavior, right? I've got 2 functions that'll trap it. Negative absolute value of x and absolute value of x. And at the center, I've put this point right there in the center where I would be missing something in the domain. So now that I've done that, I actually do have a continuous function. It's still kind of hard to draw without lifting your pencil. I mean, I can't because it's got that infinite oscillation, but that oscillation is trapped between the 2 functions. So this is actually continuous, even though I can't draw it with my pencil. So there's kind of a hint that there are things that are going to, this formal definition is going to get some things that are not quite as, you know, pretty as the draw with your pencil classic type of example. Let's look at another one of these. Remember this one. This is sine x over x. Is it continuous at x equals 0? Right? So I've got a hole there, right? Because there's something missing in the domain. Can I plug the hole? So let's look at this function. Is this function continuous? So go ahead and prove on your own that this is continuous. Just write a little short thing. And if I have a hole in a function that can be plugged, so this is a hole in a function that can be plugged. I throw the 1 in there at x equals 0, and I plug the discontinuity. That's called a removable discontinuity. And those functions are actually kind of interesting because, and we're going to see this in some of the proofs, especially the one for one of the theorems, I can't remember it off the top of my head, where you kind of just plug it. And you kind of just change the function a little bit to plug it. And then you can talk about it being continuous and differentiable, come to think of it. Okay, so those are removable discontinuities. Let's talk about what it means to be continuous over some interval, right? So I've got this idea that I want to say something about the polynomial x squared. So I have this idea that I want to say that this function is continuous everywhere, right? It's a nice little polynomial. So what does that mean? What does it mean to be continuous over an interval? Because I want to say something about functions that look pretty like this, okay? So the way I say that is I just let d be some interval. Now, f is continuous at d if for every a and d, f is defined at d, and the limit as x goes to a from the left, this is for every a and d, right? So instead of saying one a and d, I'm saying everywhere in d. So here, I'm continuous if a equals negative 1.5, if a equals negative 1, if a equals negative 1.4, if a equals 0, if a equals 0.5. This thing is continuous at every point, okay? And that's what I want to say. I want to say that f is continuous if on the interval, if for every x value in d, f is x value a in d, f is defined at a, the limit from the left equals the value of the function. Now, as long as a is not the left endpoint, right? And I'll get to that in a moment. And then the limit as x goes to a plus of f of x equals f of a, as long as a is not the right endpoint, right? So suppose D is a closed interval like 0, 1. This is this note here. So I've got f of x equals the square root of x. Now, the limit as x goes to 0 left of f of x is not defined, right? Because there's nothing left near this. But I don't care because the interval I'm interested in is 0, 1. So if I'm only interested in the interval 0, 1, it looks something like this. I'm only interested in 0, 1. As a matter of fact, let me make it so that I'm only interested in 0, 1. Okay, so if x here is from 0 to 1, I don't actually care, right? I only care about the stuff on the closed interval. Okay, so I only care about these points on the closed interval. I don't actually care about the negative side here because I'm talking about the closed interval, the less than or equal to bits from this thing. So to talk about the limit from the left as I go to 0 is nonsense. Likewise, to talk about the limit from the right, even though it would exist, right? I could make this go on and on and on. It does. Right? So I can't talk about anything here, right? If I'm sticking to the real line. If I want the square root of these negative numbers, I'd have to go imaginary. But I can talk about what's going on over here, right? With this little dashed action here, okay? But it makes I don't care. I don't care what's going on with this function to the right of this endpoint because it's a hard endpoint. Likewise, I don't care about what's going on to the left of this endpoint because it's a hard endpoint. So that's this kind of note here. If I'm talking about the closed interval 0, 1, then I don't care. At the hard endpoints, I only care about the side that's actually in D. In our example, we only care that the limit as x goes to 0 plus of the square root of x equals the square root of 0. Okay? So that's that kind of note about what does it mean? What does this little parentheses mean? Okay? That's just a side note. Okay. So what I want is the limit as x goes to a of f of x equal f of a for every a. And remember, this also means that literally f is continuous if f has the direct substitution property, right? F is continuous if and only if f has a direct substitution property. So these are all continuous functions. Just like before we had, these functions have the direct substitution property. That makes them continuous. Polynomials are continuous. Rational functions are continuous whenever the bottom does not equal 0. Sine and cosine, continuous everywhere. C to the x, continuous everywhere, I should say, where defined. So this is not everywhere. This is okay. The logs are continuous where defined. X to the c is continuous where defined. Okay, for any real c. All of these are continuous functions because they all have the direct substitution property. Okay, so let's look at something a little psychotic that kind of shows the difference between intuition and formalism, especially in this case. So we're going to see that there's a function. There's actually a ton of functions, but there is a particular one that is continuous at exactly 1 point. Okay, and it's a modified Dirichlet function. So I'm going to show that there's a function that is only continuous at 0. And that kind of breaks our intuition about the don't lift the pencil thing. Okay, so let's look at this function. The Dirichlet function is 1 if x is rational and 0 otherwise. So I'm going to multiply it by x to get this g of x thing here. G of x equals x if x is rational and 0 otherwise. So g of 1 is going to equal 1 because 1 is rational. But g of the square root of 2 equals 0 because the square root of 2 is not rational. And I've got g of pi equals 0, g of 1/4 equals 1/4, g of 1 minus the square root of 2 equals 0. And note here, there's a kind of little thing that I should say here. So I should note that there's this property of rational and irrational numbers. And it's intuitively true, right? If I've got a rational number and an irrational number, I've got something with a terminating or repeating decimal sequence and something without a repeating decimal sequence. So if I subtract that perfectly good repeating decimal sequence by something that doesn't have a repeating decimal sequence, it's just got a whole bunch of digits, I'm going to wind up with something without a repeating decimal sequence. Okay, so c minus d and d minus c would both be irrational if c was rational and d irrational. Okay, so what I want to show is that g is continuous only at x equals 0. The first thing we need to prove of this is that a is it's discontinuous at any a not equal to 0. Okay, and there are two cases of that. I'm going to have to show it works for. Let's put this in here. So I need to show it works if a is rational or if a is irrational. And then, so what I'm going to do is I'm going to make two sequences, one of rational numbers and one of irrational numbers, both heading to a in the x space, but different numbers in the y space. So if we flip back here to this idea from lecture 2a, right, I had this definition of the limit. If f is a function with a some number in or near the x space and l in or near the y space, the limit as x goes to a of f of x equals l if every sequence s, so that Sn goes to a, excluding those that are just a, or actually hit a, f of Sn goes to l. Okay, so remember, that's this idea of the intuitive kind of, I can pick a sequence here, and I can pick a sequence here, and any kind of estimate I make is all going to go to the same point. Okay, and then my count. Oops. So I want to do the same. So I can break the limit of a function if I can show that there are two sequences going to the same place in the x space, but different points in the y space. Okay, so the first one I'm going to pick. If a is rational, not equal to 0, then I'm going to let Sn equal a minus 1 over n. This is a rational sequence heading to a, right? S1 equals a minus 1, S2 will equal a minus a half, S3 will equal a minus a third, a minus a fourth, a minus a fifth, a minus a sixth, and so on and so forth, so forth. So I'm going toward a minus 0, which is just a, right? So I'm heading to a in the x space. Now, these are all rational numbers, right? A is rational and 1 over n is rational. So I'm subtracting two rational numbers, I get another rational number. That means that I'm going to use, for this sequence, I'm going to use the top definition. G of x equals x if x is rational. So this g of S1 is just S1. G of S2 is just S2. G of S3 is just a S3, and so on and so forth. So S3, G of S3, so S3 goes to A, and G of S3 also goes to A. Okay? So I'm heading to A. Now, let's look at this other thing. A minus 1 over n times the square root of 2. 1 over n times the square root of 2 is an irrational number. Okay? For every n. So f of Tn, and this a minus 1 over the square root of 2, this right here is going to go to 0. it's a minus 1 over, and I could even make this a minus n times pi if I wanted to. Okay? But all of these numbers, this number is going to get bigger on the bottom. It's going to get bigger and bigger and bigger and bigger and bigger and bigger and bigger. And since it's getting bigger and bigger and bigger and bigger and bigger, the whole thing is heading to 0. So, I'm sorry, this thing is heading to 0, which means that a minus this thing is heading to a. Tn goes to a in the x space. But look what happens to g of Tn. G of Tn, for every one of these irrational numbers, I'm going to use the second definition. So g of Tn is always equal to 0 because Tn is irrational. So this thing is 0, 0, 0, 0, 0. This heads to 0 in the y space. So I have two sequences going to a in the x space, but they go to different places in the y space. So the limit as x goes to a of g of x does not exist. Likewise, if a was irrational, it's kind of the same thing, only I'm going to choose Sn. I'm going to have f of Sn be, I'm just going to choose, okay, so if a is irrational, by definition, there was some rational sequence that goes to a. That's the definition of a real number. Remember that. X is a real number if there's some sequence that goes to x. Some rational sequence that goes to x. So I'm going to pick that rational sequence that goes to x, and I'm just going to have it be, right? That goes to a. So Sn goes to a, and so f of Sn also goes to a. Right? I don't know what the rational sequence is, but there exists one. However, the sequence Tn equals a minus 1 over n, a is irrational now, so a minus 1 over n is also irrational. So g of Tn equals 0, blah, 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 blah. So the limit doesn't exist. So for any a except 0, I know the limit doesn't exist. Now, I want to prove that the limit as x goes to 0 of g of x equals 0, and I'll leave that to you. That's on the bootleg. But here's a hint. I want to use two cops. And I want to let the top be 0 if x is less than 0, and x if x is greater than or equal to 0. And you can kind of see that here. I'm going to have something that looks like this. Then I'm going to have something that looks like this. And you have to figure out how to write up that proof. But it's a two cops proof. It's not easy, but it's not horrible. This right here, this proof that it's discontinuous is horrible. I would never put something like that on the test or quiz, but it's very interesting. This idea that I have a function that goes to exactly 1 point. That's kind of cool. All right. Let's get back to this. There's a big idea here called the intermediate value theorem. Okay, and the idea is kind of is intuitive in the following sense. Okay, if I have a ball or this thing and I toss it up into the air at t equals 4 seconds, so I toss it up some 0 feet, and at 7 seconds it's 9 feet high. So I give it a toss, and it goes up, and at some point it's 9 feet high. Okay. Was there a time when the ball was 5 feet high? All right. If I start from 0 feet and go to 9 feet, is there a time when the ball is 5 feet high? Right? Did it have to pass through 5 feet at some time in order to get to 9 feet? And the intuition is yes. And why does this work? Because the function's continuous. So let's go ahead and tell you what it is. Okay. So that's the intuition, right? There was some time when I tossed the ball up, right? At t equals 4 seconds, it was at 0. At t equals 7 seconds, it was at 9. And there's some time when there's some u here where the height of the ball is 5. Okay? Because 5 is between 0 and 9. So let's state a formula. Let d be some interval f defined on d. I don't really need it to go to all of our and A and B be two numbers in D. If f is continuous on the closed interval AB, and V is some y value strictly between f of A and f of B, then there must exist some x value u in the interval AB so that f of u equals V. And there's a lot there. So remember the metaphor and the drawing, okay? If I drop a ball from 5 feet and I grab it at 3 feet, there's some time, right? There's some time if at t equals a, I drop the ball from 5 feet and I grab it at 3 feet, there's some time when it was 4 feet high. And this is kind of the drawing to remember, right? Here we go. And there could be multiple times, right? If I toss a ball up into the air, not a ball in the air doesn't really work for this. If I have a roller coaster, there could be, whose maximum height up here was 150 feet and whose minimum height was 0. There might be multiple times when the roller coaster is at 20 feet. But at some point, right, there might be multiple times, but there's at least one time when it's 20 feet. And that's the idea. There may be multiple, but there's at least one. Okay? So here's the diagram, right? Here's F, here's A, and here's B in the X space. Now, if V in the Y space is between F of A and F of B, then there exists some time U so that F of U equaled V. Okay? And there's a couple concepts. So I just have this little diagram. Things in the X space, A, B, and U. Things in the Y space, F of A, F of B, and V. So let's use this. Let's prove that f of x equals x to the fourth minus x squared minus 1 has at least one real root between x equals 0 and x equals 2. Recall this little definition about a real root. F has a real root at x equals a if f of u equals, at x equals u if f of u equals 0. That's the definition of a root, right? So if I've got the function x cubed has a root at 0 because f of 0 equals 0. So I want to prove that x to the fourth minus x squared minus 1. There is some x so that f of x equals 0. Okay. There exists a u in 0, 2. So that f of u equals 0. My strategy is going to use the IVT. Now, so what do I need to show? I need to show, I want to use the IVT. So what do I need to show? I need to show two things. I need to show, right, f is continuous. On 0, 2. And what else? I need to show that V is some value strictly between f of A and f of B. So I need to show and 0 is between f of A and f of B. So that's what I need to show here. So the first thing I'm going to show is that f is continuous. See if I can make this work here. Okay, so I need to show that f is continuous on 0, 2, and that 0, my v, is between f of A and f of B. So f is continuous on 0, 2 because f is a polynomial, and polynomials are continuous everywhere. And 0, 2 is somewhere. So if I'm continuous everywhere, I'm continuous at the somewhere. Okay, f of 0, I need to show that 0 is between f of 0 and f of 2. So f of 0 equals -1, and f of 2 equals blah, 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 11. And since 0 is, greater than -1 this week, and less than 11, v equals 0 is strictly between f of 0 and f of 2. Okay? Thus, by the intermediate value theorem, there must exist a u in the closed interval the open interval 0, 2, so that f of u equals 0. These should have been open. Okay, so now what I've proven is that this thing has a root strictly between x equals 0 and x equals 2 by the intermediate value theorem. Okay, so today we talked about continuity and the intermediate value theorem. So let's just rehash. We went over some highlights here. We went over so we went over ambiguous infinitesimals, which I should have put on the last lecture. We did kind of the intuition behind continuity. We showed some things that were not continuous, and we had this idea that a continuous function is an atheistic white boy. It doesn't like things that are wholly or infinite, and it can't jump. Then we talked about the formal definition of a function being continuous at a point and its working definition. All right, and this is how you solve those kinds of problems. Then we talked about continuity over an interval, and I had this crazy function that was continuous at exactly 1 and only 1 point. Then we talked about the intermediate value theorem and how you prove things using the intermediate value theorem. Next week, we're going to do the definition of the derivative. That's very, very, very important. And then we're also going to, for 4b, we're going to prove the power rule. Now, you can't use the power rule on test 1. It's a test 2 concept, but you might want to watch that lecture just to see the way that the proof works, because there's going to be problems. There's definitely a problem on the bootleg that's similar, but there's also going to be problems on test 1. There's one in particular that proof, knowing that proof might be a little useful. Just saying. All right, so that's it for this week, because this is 3b. I'll see you again in 4a.